All right, so this is page 113 of the note spiral, and we're introducing a new distribution known as the t distribution. And truthfully, the point of this is to make comparisons to it and the normal because they're very, very similar. So when we were talking about the normal distribution, one of the requirements for using the normal distribution is that we had to know the standard deviation of the population. Well, the truth of the matter is we rarely know that. And so, okay, how do we handle this? And we have another distribution that's extraordinarily similar in appearance to the normal distribution, and that's the t distribution. Okay, we also talk about it being the t statistic. So with the normal, we were typically working with z equals x minus mu over sigma, or z equals x bar minus mu over sigma divided by the square root of n. That's with the normal. With a t, we're going to be working with x bar minus mu s divided by the square root of n. And you'll notice here that we have the standard deviation of the population for the normal. We're working with the normal when we're talking about this. When we have the standard deviation of the population. But here we don't have the standard deviation of the population. We have the standard deviation of the sample. Now, truthfully, for collecting data, we always have the standard. We can always calculate the standard deviation of the sample. So most of the time, we're going to be using a t as opposed to the z, but they're very, very similar. You can look at the two of them because we have a normal and we have a t distribution, and you'll notice, hey, they're both symmetric. They're both mound-shaped or bell-shaped. The t distribution, we've centered it on 0. We centered the normal on 0. And one thing you'll notice is that the normal distribution is a little bit taller, and the t distribution is a little bit fatter, a little bit shorter and fatter. The t distribution has more area in the tails, all right? And one of the other things that's really big, obviously it's a big deal that this is a standard deviation of the population, this is standard deviation of the sample. The other big, huge difference is, besides having more area in the tails, is the normal distribution, every single one of them basically follows the empirical rule. We can always use the z, and regardless of the sample size, it's going to be plus or minus 1 is 68% about, plus or minus 2 is about 95%, plus or minus 3 is going to be 99.7%. That's not the case with the t distribution. There is a different t distribution for every sample size. We actually talk about degrees of freedom, and degrees of freedom, and I'm just going to abbreviate it as df, equals n minus 1. So the sample size minus 1. So for every single degree, every single sample size, we have a new t distribution. It's not determined by the standard deviation. It's determined by the sample size. Okay, so in other words, there truly is an infinite number of t distributions, but it's not a big deal because our calculator will handle that for us behind the scenes, and it's really just as easy to use as a z distribution. All right, as part of our components, x bar is just the standard deviation of the sample. That's the standard deviation of sample. That is the mean of the sample. Here's the mean of the population. Standard deviation of the sample divided by the square root of the sample size. So, as I said, there's a different t distribution for every degree of freedom, or in other words, every sample size minus 1, there's a new one. They're centered at 0 and symmetric at about 0. The area under the curve, of course, is a probability density function, so it's 1, just like it would be for any other. Now, one thing, as you increase the sample size, it gets closer and closer to the normal. It approximates the normal, but it never becomes normal. So if we are using the standard deviation of the sample, if we're using the standard deviation of the sample, we should always use t. And like I said, reality is we rarely ever know the actual population parameter. We rarely ever know this, so we usually have to use the standard deviation of the sample as an estimate. And because it's an estimate, the t is wider or has more variance or more area in the tails than does the normal. All right, so the t distribution has more area in the tails than the normal, or in the t distribution has greater variance than normal. So, all right, we know that there's going to be restrictions as when you can use the t, just like there's restrictions on when you can use a normal. Okay, we can use it when the data is nearly normal and the standard deviation of the population is not known. Okay, if the data is nearly normal, and we test it by drawing pictures, actually box plots or other graphs, if it's nearly normal or close to normal, it's okay to do it if we have a sample size less than 30. All right, but if when the standard deviation of the population is not known, because remember, in both cases we're using standard deviation of the population is not known, so we're using the sample standard deviation. So if we're using the sample standard deviation and the underlying data is not normal, the sample size must be 30 or larger, just like it had to be 30 or larger for us to use central limit theorem. So if the underlying population is approximately normal, we have the standard deviation of the sample, we're using the standard deviation of the sample, it's okay to use the t. On the other hand, if the underlying population is skewed or bimodal or uniform, in other words, it's not normal, we need to have a sample size of 30 or more. All right? The t distribution should not be used with small samples, in other words, n less than 30, unless the underlying population is normal. And I put a huge big star by that. That's really important information. And by the way, this page is full of important information, and you need to make sure that you're very clear on this. Once again, the t distribution is using the standard deviation of the sample. And because that's an estimate, it's going to be wider and have more area or more area in the tails and more variance than the normal. In addition, the t distribution, there's a different t distribution, a different set of probabilities associated with every different sample size. So I'm going to make a quick comparison between the two, and I've actually done all the work here to speed this along. So if we have a normal distribution and it's centered about some mean, and we have a t distribution centered about some mean. Well, when we do the area at 68%, you're going, oh, that's plus or minus 1. Well, that's, as we know, that's really just an estimate. So let's calculate what that z-score is. Well, that z-score is going to be second vars, inverse norm, and the area in this case would be parentheses 1 minus 0.68, because we're centering it about the mean, divided by 2. For all z-scores, when we're working with a z-score, 0 and 1, and we calculate, and we end up getting 0.9944. All right, so 0.9944. Now, if we happen to have a standard deviation of 5, it ends up being 0.994 times 5 divided by the square root of 4. Because we have a sample of size 5, our standard deviation is 5. So basically that tells you, hey, you know what? Right here would be negative 2.486. This would be 2.486. And this would be centered about 0 in this case. If I go to a 95% confidence interval, I end up getting 1.96. And please notice this right here is the same for each one of them, because it's the standard deviation of the population divided by the square root of the sample size. So in other words, we're employing central limit theorem, and we're just saying how far apart or how spread the data is. So if I did that again, I'm going to go ahead and do it for 95%. Second vars, inverse norm, parenthesis 1 minus 0.95, because I'm centered about the mean, divided by, oops, I didn't get my parenthesis 1 minus 0.95, close parenthesis, divided by 2. Having a little trouble pushing the buttons this morning. And once again, I get not quite 2. We estimated at 2, but we're plus or minus 1.96. So in this case, times our standard deviation, and we get 5 divided by the square root of 4, and we end up finding that, oh, now we're out 4.9 below and 4.9 above. So right here, this would be essentially negative 4.9. This is positive 4.9. And if I went to 3 standard deviations, this is about negative 7.4, and this is positive. That should be up here, 4.9, and this is positive 7.4. And we know that 99% of the data is between here and with this one, 95%, and right here, we have 68%. Let's compare that to what happens when we work with a t-distribution. So here we were working with a standard deviation of 5. Here we're going to, the population. Here we're going to work with the sample standard deviation of 5. This had a sample of size 4. This also has a sample size 4. So in this case, we're talking about degrees of freedom. Because remember, degrees of freedom, as I said earlier, is just the sample size minus 1. So 4 minus 1 is degrees of freedom, in this case, is 3. And just to be consistent, I did that all the way down. And I want to show you how much wider or how it varies if we make it, if we adjust the size of the standard, if we adjust the sample size. When we go from, if we adjust from a normal to a t. So in this particular instance, we have 3 degrees of freedom, but we're working with essentially the same standard deviation. This is the population. This is an estimate here using the t. Here is the same sample size. So let's try this out. Now, we don't get to use inverse norm because we're working with a t distribution. So we're going to go second vars, inverse t. It's all right. So I have inverse t. And I'm going to go area. Once again, I'm doing the same type of calculation. Parenthesis 1 minus 0.68, close parenthesis, divided by 2. Degrees of freedom, which was 4 minus 1, or just 3. You can type in just 3. There's no reason to do 4 minus 1. That's what it is. And we end up finding that our t-score is 1.188. Compare that to over here. Notice this one is a fair amount wider, all right? And so when I calculate it, instead of being 2.48, I'm 2.97. So basically the t-distribution is more spread out. This is further apart from the mean than the normal. And that's the big difference. And if I did it again, we find that this one is at 7.9, negative 7.9, and I'll show you how I did that in just a second. And this is positive 7.9. Notice this was at 4.9 and this is at 7.9. Obviously, we're getting a fair amount larger. And look at this. This is at negative 22, and this is like, oh, this is only at negative 7. So you can obviously see that the t-distribution is more spread out. So second vars, inverse t, and I'm going to do the 95% real quickly, parenthesis, 1 minus 0.95, close parenthesis, divided by 2. And I kept my degrees of freedom at 3. Oops, I have an issue. Second vars, inverse t. 1 minus 0.95 divided by 2. Degrees of freedom. Well, how did that happen? Oh, that's correct. 3.182. All right. So obviously we see that instead of being at a little less than 2, we are a little more than 3. We went from a little less than 2 to a little more than 3. Here we went from just under 3 to almost 9. Okay, just under 3 to almost 9. So obviously the t distribution is much wider. Now you're probably asking yourself, once again, you're going, well, if I have more variation, why would I use the t distribution? And the reason you use the t distribution, and you have to do this, if I'm working with the standard deviation of the sample, I have to use the t distribution. If I happen to know the standard deviation of the population, I can use the normal and the z. But if I don't, I have to use the t. The bottom part of the page is doing the same thing, but it's actually using, instead of a mean of 0 or just a mean, we said let's do a mean of 3. Okay, and I'm going to just real quickly do something here. This is just doing the same thing, but instead of being centered on 0, we centered it on 3. Same thing here. And so you go, oh, okay, this is at 0.022. This one right here is 0.027. This is 5.97. So 68% lie between here, and 68% lie here. I'm going to show you a really quick way on the calculator, because this is going to come in and help you out later on. But let's show you real quickly. Second vars, stat, test, and I'm going to go to a z interval. Let's look at number 7. So choice number 7 is z interval. And I'm going to press enter. I want stats to be highlighted. My standard deviation happened to be 5. We said in this particular case, the mean, actually the mean on this case we said was 3. X bar is 3. And my sample size was 4. And I want to do 68%. I want an area of 0.68. And I end up getting 0.5138, 0.5486. It did this calculation for me behind the screen scenes. Let's do that again real quickly. We'll do it for the 95%. Second vars, stat, test, and we're going to go to number 7, which is a z interval. And we're going to go 5, because our standard deviation is still 5. We're still setting it up on a sample mean of 3. Our sample is still size 4, but we're going to change our confidence level to 0.95. In other words, we're going out plus or minus 2 standard deviations. And so it did all the work behind for me and gives me negative, oops, I'm sorry about that. Did all the work before for me at negative 1.9 and 7.9. I'm going to run through that real quickly again, just because I had that pushed off the screen. Sorry about that. So second quit, stat, test, number 7, which is z interval. My standard deviation is 5. My sample mean is 3. My sample size is 4, and my confidence level is 0.95. And I just pressed enter, and there it is. It gives me that width. Now, obviously, I could have done that for 3 standard deviations as well, or for 99.7. Let's compare that to the t. So I'm going to go stat test. Well, we're no longer using the z interval, which is number 7. We're going to use number 8, which is the t interval. So we have our x bar is 3, and we need the standard deviation of our sample. Well, our standard deviation of our sample is 5, and our sample size 4, and we're going to do this 0.68. Now, when we do a confidence level, it really means it's centered about the mean. So it already centers it for us, which is kind of nice. And we find out, oh, it's 0.2277 versus 5.97. If I go back and I do the same thing, we're going to go back to number 8, and we're going to change this level to 0.95. And when I look at this, I'm now at negative 4.956 to 10.956. Now, compare this to what we have. This one, these two, this one's a little bit wider, but not a whole lot wider. I get to here, and this is almost to -2. This is almost to -5. Wow, this is 7.9, and this is 10.9. Obviously, the t distribution is wider and more spread out than the z. And by the way, how did I get here real quickly? I did stats, test. This one was a number 8 z interval. And this is a number 7 z interval. This is a number 8 t interval. All right. So that will conclude this particular video, and we will work some more with it in just a moment. Continue working with the t.